Dan Shagru here. Thrilled to be able to demonstrate the new checksum enhancement to our ARM protections. So way back in our Denali release, we announced the availability of post-build, or otherwise known as ARM protections, for enterprises who wanted to take advantage of simpler CI setup and protection configuration for iOS. As of Erawan, we've greatly strengthened those post-build protections and are happy to announce that our latest ARM protections include usability improvements, such as the ability to more easily optimize security against performance, the ability to perform checksums dynamically, which is what I'm about to show you, as well as new string encryption. In addition, we've improved the ability to protect MAUI apps by adding protections for DLL files. So let's see the new checksum guard in action. Stephen Friedman is going to step you through this. He's going to first show an app that is working as it should on an iPhone. And then he's going to show how an attacker would manipulate that unprotected app. And the attacker, in this case, will successfully manipulate it. And then we'll show an unprotected, manipulated app successfully running on an iPhone. And then finally, we'll show a protected, manipulated app being successfully stopped from being run on the iPhone. So here goes.
This is Stephen Friedman, and this is a demo that's going to show modifying an iOS binary application with malicious intent and integrity checks using the checksum guard of ARM protection. So to start, I have a mirror of an iOS device on my screen so that you can see it, and I have an application named Job Dispatcher. And this application has a login screen in the front. Now if I use tech as my username and I just put in a wrong password, it checks that and shows there's an invalid password. If I put in a correct password, which in this case is the word secret, and you can't see it on the screen, but I am typing it in, then it does log in successfully. And so what I want to do is take on the role of an attacker that's going to try to bypass this basic check. And to start, why don't we look at the source code to understand what's going on and what I'm trying to do. So I have this basic login function named authenticate. It takes a username and a password, and then it uses the is=string function to check the username is tech and to check that the password is secret. Now this is not how real logins work on full applications that are released. However, this is very similar to a lot of basic functions that do some kind of check for a valid state and then continue on. And so we have the strings tech and secret, which someone could look for, but an attacker might look for similar ideas like an error message for an invalid password or an invalid license or some other kind of check they might do on a real application. But the attacker doesn't have this source code at all. So let's jump to what the attacker might be able to see. And they might use a tool like Ghidra. And so Ghidra is a free and open source tool which can take a binary application and disassemble it from ones and zeros into human readable assembly, which is what we see in the center, and into decompiled C-like code, which we can see on the right. And it might start us off at this entry function, which is where we start executing inside of this application. But I want to find the actual function that I'm looking for the authentication. Now let's say I know that there's a username of tech that's accepted. And so I can search for strings and then search for the word tech. And I can see that there is one string for the word tech inside of this application, and I can jump to it in this main window. So I see here, it looks like I'm in the C string section, text part of my text part of my binary, and then we have two strings here, the string tech and the string secret. Both of these have a cross-reference to another part of the code base. So why don't I jump to that? And from here we can see what looks like a wrapper around the string that contains some extra information. But the important part here is that this wrapper for text is used in a function, which Ghidra is naming a function that's at this address, because it doesn't know the function name. the word authenticate is not stored in the application. So let's take a look. I'm going to look at the decompiled code on the right first. Let's see. Does this look like it might be our function? It takes two parameters. It looks like it's calling some helper function and doing a basic check, and then calling the same helper function. Just dig in a little more. Let's jump into this helper function. And we can see from looking at it that it's actually making a call into is equal to string. So I think we're in the right place. This is the authenticate function that we're looking for. Now let's take a closer look at this assembly. I want to find a way to bypass this password check. And so I know that there's a string of secret that gets used, and it looks like it's being referenced somehow in this register named x2. It gets loaded. This is calling a helper function, which is comparing strings. ARM64 is always going to store, or usually going to store, the return value in this x0 register. And it seems like this function is then moving that return value into x20. So I could bypass this entire string comparison if I just make sure that whatever gets copied in the x20 is always the same string, or at least it thinks it is. So in that case, this is a Boolean function, and if it's the same string, it returns yes. And so this move, x20, x0, is this binary hex code on the left here. Starts with F4 and goes on. And I want to figure out what's the binary that I need to put in that location instead. So I'm just going to use this website that can do this conversion of ARM64 assembly code back into binary. And what the assembly code that I want is a move instruction into register 20 of the constant value of 1, which will represent yes in the booleans. And I have it right here. So this is the hex code that I need to be that value. So I know what I need to change it to, but where is this in this actual file that is the binary? And Guija points to it. It's actually this address right here. So the one in the front is actually an image-based offset that Guija is helpfully showing us. When you look in the actual file, it's going to be this 4040 hex address. So I know the location, and I know what I have to change to disable the check. And then from here, I wrote a Python script that goes into these binaries, opens up the IPA, modifies this move instruction with the one we want, makes it so it's always true, and then saves it back up. So let's go ahead and run that. And this is going to make two versions for me for convenience. One version is showing a modified version of an unprotected application. The second version is using integrity checks from wire protection to protect the application, but it is still getting modified. So I have my two versions. Now, I made modifications to the binary, and so I have to re-sign it. So let me go in and just re-sign these applications really fast so that I can run them on my iPhone. And I have a unprotected version. Let me go ahead and sign that one first. And I'll save this on my desktop to notate that it's unprotected. And then I'll go ahead and re-sign the protected version as well. And I'll notate that this is the protected version. Okay, my applications are re-signed, and now I can run them on my device. Okay, so this here is the Xcode device viewer. Let me go ahead and uninstall the version that I had and install on my desktop this unprotected version. Now I have a new app. And I can take Job Dispatcher and open it up, put in my username, it's still tech, but I can type in any garbage password that I want and hit login, and it works. So I didn't type secret there, I actually just hit a bunch of random keys. That's not good. We managed to just fully bypass the check by changing one small line of assembly. But if I have a protected application that has integrity checks for ARM protection, and I do the same thing, and I run that application, it's actually running the checksum guard to make sure there were no modifications of the binary, and it runs that right at boot up. So it doesn't even finish loading the screen. It checks, it knows the files are modified, immediately crashes the application, the attacker gets nowhere. And that's the value of the checksum guard against binary modification.
That's it. For more information, please contact us at digital.ai. We look forward to discussing with you how we can help you secure your apps against reverse engineering.